Okay, guys, so we're going to continue the conversation we were having yesterday. And that's thinking and envisioning complexity. We're going to leave the conflict stuff behind for a bit and do again, embrace again the climate problematique. And then kind of reconnect all three at the end. Okay, so we made some interesting points yesterday about the political and the economic as being critical components of complex maps, complex systems theories, and I just totally agreed. So I thought I'd start with this observation that I think the references yesterday to what we refer to as the knowledge action gap really does lie in a great deal of ignorance. Unfortunately, some of it, if not a good chunk of it, rather willful ignorance even, right? So let's start with a quiz. Thought that'd be fun. Guess who said this terrific little one-liner? Trees cause more pollution than automobiles do. Yeah, you can't make this stuff up, folks. So who do you think said it? I'll give you guys a second, right? Okay. I bet some of you are thinking, that guy. Remember Mr. Siegel? Good guess. But wrong. It's not him. But man, I really wish it were, because the truth is so much worse. The author of those words, Ronald Reagan, 40th President of the United States of America. You want to know why, Lee? I think you were raising the question yesterday. We don't make more progress, given the insights and the leverage that complexity theory can provide. It's crap like that. So, it's about complex thinking that we have to win people over to, I think, right? And get them out of their vested interest, which is not a winning proposition, really. So the idea I wanted to try to make yesterday, and I want to kind of just restate today, is complex thinking, or complexity thinking, I should say, is about thinking big. And I mean that kind of in very literal ways, right? We can conceive of the way we need to be thinking in terms of scale and scope and magnitude, right? The scope of our thinking kind of speaks to the breadth, the depth, the width. How wide and far do our ideas range? The scale kind of speaks to the level at which our analyses reside. And in complexity thinking, the scales are big because we often, it's the very thing that won Anomaly the Nobel Prize this year, connecting multiple levels of analysis. So his work connecting atmospheric conditions with surface temperatures in the ocean and land, it's that interconnectivity at different levels of scale that is, and then magnitude is just about the kind of quantitative dimension of things that we want to know about, like yesterday's discussion, of course, of the magnitude of conflict. To give examples of saying yesterday, examples of this is thinking on a planetary level, right? The scope of our thinking needs to be planetary, and this is really quite different from what we're expected to do in the course of our daily lives, right? And so I've got a kind of an approach to help you do planetary scale thinking, and I hope you find it useful. I had a good time putting it together. It's next. We need to think in geological timescales, not kind of 24-hour periods as we might do, or less so even. Very, very long timescales. The geological timescale goes back, 4.5 million years. And the data I've been running this past couple of weeks, is in the context of an 800,000 year period. So, we're big time frames, right? And then lastly, our models, our explanatory models are just multi-dimensional beyond what, we just really ever kind of confront in our standard approaches to things. So to get you to kind of think in planetary terms, to begin to grapple with these complex problems of scale, scope, and magnitude of climate change, we've got to think on a planetary scale. So, do you see it yet? Planet? No? See it now? What is that, you think? That's a famous pale blue.
Consider again that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. Every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust, suspended in a sunbeam. The earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals and emperors, so that in glory and triumph they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. Like it or not, for the moment, the earth is where we make our stand. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.
Carl Sagan was a pretty marvelous person. That was the basis for one of his books that he wrote, and I thought it was a nice way to begin getting you to just naturally conceive of where we need to lay our minds, as it were, right? And seeing, our home planet, everything that we know that seems so vast, in that way, revealed in all of its insignificance, its tininess, I hope helps you think in planetary terms, or on a planetary scale. Here's another way to try to get you to do that. Let's think about the four inner rocky planets of the solar system: Mercury, Venus, Earth, and Mars, right? Given the centrality of the sun, given that the sun is the sole source of heat in the solar system, right? Can you predict the order of these four planets in terms of their temperature, from coldest to hottest? Which one would be coldest, and so next, and then towards the very hottest? Let's see how you do, right? I'll give you a second, kind of just sort of imagine who you think they are. If logic were at work, or if the obvious were the explanation, we'd have quick work of this. But unless you know something about solar system, you might not get this, right? So let's see what we've got. We've got, in terms of distances, right? Mercury is obviously the closest. It's only 58 million kilometers from the sun, right? And Venus is next at 108, so about almost twice that distance. We're about that and a half again. We're 8 light seconds away. Light travels at 300,000 kilometers per second, and it takes the light from the sun 8 seconds to get to Earth. So that's how far we are. And then Mars kind of jumps out to almost two and a half million kilometers. So given just the distances and the sun being the sole source of heat in the solar system, I would have predicted, right, that Mars would be coldest, and then just on in, Earth, Venus, and Mercury would be the hottest, right? It's only partly true, right? Mars is in fact the coolest. Earth is in fact the next coolest. But it's Mercury, actually, that is second hottest in some respects. It's Venus that is the hottest and you're going to see in a very interesting way, right? So Venus wins the prize. It is, far and away the hottest planet. I mean, Mercury averages 140 degrees Celsius. The Earth comes in at a nice, cool 23.5. 465. And you're going to see that, boy, that's a dead-on, kind of figure. But the question is why, right? If Mercury is only 50 million kilometers closer to the source of all the heat in the solar system, why isn't it the hottest, right? Well, that's why we need to talk about climates, right? And atmospheres, okay? So let's talk about planetary climates, right? And I'm kind of just hoping that talking in terms of other planets will help us think in a planetary scale in our own world. So we've got the 4 planets laid out here. Now, we've got temperature fluctuation, except on Venus, right? As I said, that number for Venus, 465 degrees, is the temperature on Venus, right? I mean, it really does not change, right? We've got fluctuation, ranging, in quite a broad, to a broad degree, right? We've got 0 degree variation or fluctuation in Venus, right? It averages 465 degrees all the time, right? On Venus, right? Mercury, right? Okay, now it does get hot, right? I mean, it is quite close to the sun, so it cranks up at 449 degrees centigrade. But it's also, right, reaches the coldest temperature of any of the 4 inner planets, right? So it's very hot, but also the coldest of the 4, right? Why is that? Well, you might kind of imagine that it's got no atmosphere, right? So the side facing the sun that's so close is just scorchingly hot, and the side that's facing away is freezing cold because it's getting nothing. So yeah, Mercury gets hot, but it also happens to be the coldest of any of the other 4, right? So what is up with Venus, right? Because it turns out that scientists don't think Venus was always this miserably, constantly, invariably, insanely hot, right? In fact, the kind of creepy thing, really, is that Venus seems to suffer from the very problem we're trying to avoid here on Earth, what we might call, or what does get called, a runaway greenhouse effect, right? A greenhouse effect is not a bad thing, right? But you heard the expression, you can have too much of a good thing. That's a runaway greenhouse effect. And we already have too much of a good thing in our own greenhouse effect. What we want to do is not end up, celebrating, our winter holidays at 465 degrees Celsius. We want to turn things around before we get to what we're going to call a tipping point later, and rein in the forces that are trying to unleash our greenhouse processes and dynamics into a runaway model. So the core dynamic in climate change is the greenhouse effect, right? And it's a simple idea, but we're going to listen to a little story. But the greenhouse effect, right, is stuff that we know intuitively, right? I mean, the sun comes in, warms it up, and not all of the sun's heat escapes back out into space. Some of it's caught, thankfully, right, by these gases, gases in methane and carbon dioxide, most importantly. And in catching some of that heat that's bouncing back out into space, it keeps the Earth warmer than it would be, and it makes life possible, frankly. Right? So just like a greenhouse, right? It makes possible to grow those hothouse flowers in the midst of very cold climes. Right? So greenhouse effect is a good thing, and I want to make sure that's clear because we tend to talk about it only in a negative context, right? So the greenhouse gases prevent heat from escaping into space and warming the planet, right? I want us to realize, right, because there are those folks like, and I don't mean just the Jason, whatever his name is, but there are a surprising number of people who are unaware of how firmly established all of the fundamentals of climate science are and for how long they've been established. So the phenomenon of the greenhouse effect was first theorized by Joseph Fourier in 1924, right? And by mid-century, right, we had very good predictive evidence that the greenhouse effect was in fact an absolutely indisputable, unarguable part of our scientific knowledge. We knew why the Earth was warmer than it would be otherwise, right? Thanks to the greenhouse effect. So let's kind of look at this a little more closely. Right? Welcome to the Anthropocene.
The main cause is a phenomenon known as the greenhouse effect. Gases in the atmosphere, such as water vapor, carbon dioxide, methane, nitrous oxide, and chlorofluorocarbons, let the sun's light in, but keep some of the heat from escaping, like the glass walls of a greenhouse. The more greenhouse gases in the atmosphere, the more heat gets trapped, strengthening the greenhouse effect and increasing the Earth's temperature. Human activities, like the burning of fossil fuels, have increased the amount of CO2 in the atmosphere by more than a third since the Industrial Revolution. The rapid increase in greenhouse gases in the atmosphere has warmed the planet at an alarming rate. While Earth's climate has fluctuated in the past, atmospheric carbon dioxide hasn't reached today's levels in hundreds of thousands of years.
We think in these long terms, right? We need to be thinking in these long geologic timescales, right? And in doing so, a kind of peculiar thing happens to the climate narrative, to climate discourse. For some, taking that long-term geologic time scale helps them kind of deny or mask the evidence of anthropogenic climate change, right? Because when you look at 800,000, sorry, I think I have a delivery here. So as I was saying, when you look at a time scale of 800,000 years, it's almost guaranteed, or longer, right? If you use the whole, well, we're going to go into a minute into the kind of geologic periods that we're in at present. But if you look at 800,000 or 2.8 million years, there's an almost absolute certainty that one will find a history of climate fluctuation that can be used by those with an interest in doing so as part of an argument against the evidence, the scientific evidence of anthropogenic climate change today. So there's an odd sort of occurrence that happens when we take the necessary required long-term view of things, the geologic timescale, we're almost certain to find evidence of past climate shifts. It's just that we know now the science of the greenhouse effect. We know the complex dynamics, the feedback loops that push an atmospheric system, an ecosystem, to what we'll call here shortly a tipping point, and past it, which is what happened to Venus, which is why Venus is an uninhabitable, hellish, nightmarish, blisteringly hot all the time place. It's not as close to the sun as Mercury, but it's almost 3 times as hot. And it's due to the runaway greenhouse effect that has taken place on Venus for reasons that we don't know. So, okay, so speaking of greenhouse effects and gases, let's meet our friend carbon dioxide. I mean, the greenhouse gas par excellence. We're going to spend some time, as I said before, I've spent a lot of time, like an irrational amount of time, but I have kind of geeked out on this for the last couple of weeks. I've really found it fascinating to just dig into the data and see what's there and find out what I can find. So we're gonna spend some time talking about CO2 data, and then we're gonna talk about temperature data and some sea level data, and then we're gonna kind of combine those 3 things and see what happens. Reminding us again of the need to get that proper beat on time scale. So we are presently, in what geologists refer to as the Quaternary, right? Which is, it has to do with the Latin root of quarter, and it's the kind of dividing into 4 big epochs. But we are in the kind of a novel epoch, geological epoch, because it's one that's been given a name by those who don't normally engage in the naming of geological epochs. But officially, right, we are in, there are 2 periods to the Quaternary. There's the Pleistocene, which goes from about almost 12,000 years ago, at the end of the last ice age, to about 2.5 million, 2.78 million years ago. So the Pleistocene's, back to, say 2.8 million years, up to about 12,000 years ago. And then about 12,000 years ago, we started the Holocene, and that takes us to the present, and those 2 constitute the Quaternary. You really have to kind of, what we're going to do with that is, when you put, when we talk about 2.5, 2.7, 2.8 million years, that seems like an enormous amount of time, and it is a lot of time, right? But when you get into the geologic timelines of the Earth, the Paleolithic, the Mesozoic, and on farther back, you're talking about some real time. So let's look at what happens when we adopt this longer term outlook. The first thing that we'll notice on this slide is that as we probably would have guessed, right, levels of carbon dioxide in the atmosphere have increased, and have increased rather precipitously, rather quickly. And it's important that we see the both degree of increase and the speed, or the time, the short amount of time that it's taken to get that increase, and how much of a difference or an abrupt change that is from a very, very, very long established CO2 pattern in our atmosphere. Okay, so that's what we're going to see. What we have just seen is this kind of moment at which CO2 levels begin to rise above a zone, an average, kind of a, you can see right there in that chart that that moment from the video we watched by Neil deGrasse Tyson on the difference between weather and climate. Remember the kind of patterns, those cyclical patterns. Well, those are actually even climate patterns because we're talking about 800,000 years. But they cycle within a band, right? Okay, and we're looking at CO2 data, right? So, and this is of course using the fossil records and all that kind of stuff, and core sampling and all that. But what we see is an observation in the year 2011 that CO2 levels in our atmosphere were almost 400 parts per million. Okay? That turns out to be just about double what has been the historical average for our atmosphere for a rather long time. How long? About 800,000 years. Okay? That's right. So for about 800,000 years, almost a million years, okay, CO2 levels have stayed within a band quite narrowly around 200 parts per million. And within a span of about 150 years, about 170 years, we jumped to twice that, right? About 98% increase in about 150 years. So it's really an extraordinary increase in such an extraordinarily small amount of time. How much time? The time it took to double what had lasted for 800,000 years was just 0.02187% of that period of time. In other words, a fraction of a fraction of a fraction of a moment was all it took to double what had lasted for 800,000 years. If we want to see just how brief a span of time it took to double the long-standing average or mean level of CO2 in the atmosphere, take the whole Pleistocene era to back to 2.8 million years, and then we're talking about an increase, doubling the amount that had been, persistent in our atmosphere, that really accounts for 0.0038% or 3/10,000ths of 1% of the Pleistocene era it took to double what had lasted for almost a million years. That's an extraordinary shift. That's a transformation of a significant size, scale, and at a speed that is just, on a geologic time scale, lightning quick, lightning fast, right? And it is as we'll see when we talk about the tipping point and the graphical representations of a tipping point, it is the speed with which these changes take place that makes prediction really complicated, and that can introduce all manner of frightening elements. Okay, so just a bit more. So again, kind of just recap. In 2011, right, we observed a carbon dioxide level that was a 98% increase, almost double, over the 200 parts per million average that lasted for 800,000 years, right? And again, right, it took just a lightning fast amount of time to accomplish that, right? If you compare the 175 years when the CO2 levels started to seemingly irreversibly rise with the period of time at which 200 was the average, again, that figure was 0.003, right, of 1%, 3/10,000ths of 1%. It's just insane. I don't even know how to speak those small numbers. Okay, Forecasts, and we're going to do some of that, and I've been doing a lot of that lately. For the year 2100, for the next century, is something that climate scientists spend a lot of time doing and perfecting their craft and getting better and better. And again, I highly recommend taking a peek at Nate Silver's book on and his discussions on prediction. But the forecasts for the year 2100, which is now really only less than 80 years away, right? Forecasts for the year 2100 have a range of 440 parts per million, which is just a little above where we are now, to double, basically, 880 parts per million, which would be 2468, 4 times, 400% the average that lasted again for almost a million years, right? That's a pretty big range. Right now, we've seen yesterday why it is that forecasts might have that kind of broad, depending on the standard deviation of your observations and that sort of thing, that you'll get that kind of spread of possibilities. But remember why this matters. Remember that Runaway, who just won the Nobel Prize in Physics for this stuff, proved that carbon dioxide and temperatures on the land and in the ocean are what are known as recursively causal, right? They are interactively causal. They can cause each other to shift and change, right? It is the interaction of CO2 with other components of the climate system that help us understand variations in land-ocean temperatures, changes in land-ocean temperatures. So what would then, the question seems to be, right, obvious, is what would an increase to, again, another doubling basic, or no, just a slight increase to 440 parts per million, to a doubling again to 880 parts per million mean for Earth's temperature, given that we know that the levels of CO2 are positively and strongly correlated, in fact, they're causally related to Earth's temperature via things like ocean levels and things like that. Okay, so what do our predictions, our forecasts and you'll see that my own forecasts are in this range. They're a bit less than they're a bit less than the high of 880 and a bit more than the low of 440, which I think is kind of good. And I will tell you now, the statistical significance of my test came back so strikingly affirming that I just figured I had to have done something wrong, and I sent it out to more experienced colleagues on this stuff, and it turns out I've done okay. So you'll see then my own kind of comparative work on prediction and predicting things like future CO2 levels, future temperatures, things like that. Okay, so let's take what's one of the kind of the best known forecasters and best known complex systems modelers using computer simulations is Professor Hansen. I think it's at Caltech or something. So I've got Hansen data, which has CO2 levels, average Earth temperatures, and sea level in meters, right? And you can kind of see a glimpse of that data before you, right? And you can see that his simulations are so well known because they do one thing that they do is they post-dict. It's called post-dicting. It perfectly almost explains past behavior. His models that are generated in front of you help explain past behavior so perfectly well that we have high levels of confidence that their predictions of the future are quite solid. So his simulations and complex systems of agent-based modeling are indeed considered among the most sophisticated in the world. So Hansen data is quite good, quite significant. So we've got this kind of perfect correlation, this r squared equals 1 in that ideal world, between CO2 levels and temperature. We've got the same between CO2 levels and sea levels, the level of the oceans that are rising and threatening coastal populations and things like that. And then temperature and sea levels, of course. The Wannabe's kind of contribution there. So that's the kind of simulations and the simulation that Hansen's famous for. So what I did was take Hansen data, that the kind of the red numbers there, and then I extrapolated from that into the future to try to see what the predictions of the forecasts of CO2 levels of 440 and 880 mean for, or would mean for our climate. So I use existing data, extrapolate from it to do some forecasting. And let's kind of take you through the process here. So first thing I'd point out is just, what is temperature? Now, in a little bit, the most of the temperature data I'm going to work with isn't actually stated in degrees of temperature. And what we tend to find more useful is what's called temperature anomaly data, right? So what we do is we take readings and record the degree of change in average temperature from month to month. So the data set one of the data sets I was working with has monthly, 12 months a year, average change in the global mean temperature. Some months, the mean global temperature would decrease by a fraction of a degree, on occasion a degree, or even on a rare occasion more than a degree, or go up by those same margins. And it turns out that it's more useful for numbers of reasons, a lot to do with the quality of the data, to use those kinds of numbers rather than actual temperature data, which is what I have in front of us. But I thought it was useful to start with this. So first, appreciate that the 20th century was, of course, the warmest century on record, and every decade towards the end of it was increasingly the hottest decade on record. And if I remember correctly, we are now still 7 of the last 10 hottest years on record have occurred within the last 10 to 12 years. So we're getting warm, and we're getting warmer, and we're getting warmer at a pretty frightening pace. So the average temperature for the 20th century, now this is the global whole, remember we're thinking in planetary scale, blue dot, right? Is 14.5 degrees, right, Celsius. The median, the middle, it's so similar to a mean or an average, is 14. And the standard deviation, given what we talked about yesterday, the standard deviation is almost 1.5 degrees, right? So what that simply means, the standard deviation is useful for us, right? It tells us if this were normally, and temperature data tends to be fairly closely normally distributed, that given an average of 14.5 degrees and a standard deviation of 1.5 degrees, that means that about 68% of the observations of temperature fall within the range of 13 degrees to 16 degrees. Okay? And about 86% fall between 2 standard deviations, or 3 degrees below and 3 degrees above the average of 14.5. So 11 and whatever. So it's pretty real, but that standard deviation helps, remember, as we were talking yesterday, understand in conjunction with confidence intervals the range of prediction outcomes that are associated with forecasting. So what do we see when we get to a CO2 level of 440 parts per million? Well, that's this first one, right? And using the Hansen data regression line, we get a temperature of 22.5 degrees centigrade. And that's at 440 parts per million. That's not a far cry from where we are now, which is about, I think, 418. I'll have to looked at it, but I think at present it's about 418, 420 parts per million. So 440 is hardly a monstrous leap from where we are when we compare, for example, that we doubled from 200 to 400 what had lasted 800,000 years, and we did so in a span of 150 years, right? So getting to 22.5 degrees is a 60.71% increase in the median temperature from the 20th century average. That's a planetary killer, basically, right? And if the forecasts that predict an 880 parts per million level of CO2, well, you can just imagine that is indeed a level of CO2 that accounts for the final extinction event, the last. There will not be civilization remaining. The temperature associated with an 880 parts per million CO2, barring truly astonishing, miraculous technological developments that could capture carbon at that kind of necessary level, is associated with a temperature of 44.5 degrees centigrade. Folks, that's just simply a planet killer. That's an increase of 217.85% increase over the median temperature of the 20th century. That kills all life on the planet, right? That goes past the tipping point. We'll talk about that in just a moment, and puts us squarely in the neighborhood of runaway greenhouse effect. And cancel Christmas, cancel Eid, cancel Hanukkah. It's end times. Right? So we want to avoid that sort of outcome, if at all possible. All right. Now, to assuage fears, there are those who just don't like data. Remember that Jason, whatever his name was. They don't trust other people's data. They don't trust, the use of this data set or that data set. So what I've been doing these last few weeks, besides just geeking out on this, is combining data sets, using from different, first-class sources, NASA, NOAA, just so great data, right? But combining them for my purpose. So I might use temperature from NOAA and CO2 levels from NASA, for example, just to kind of and then use their own individually to do, and it all affirms they're all doing good data analysis, good data collection rather. I will have to say that some of the findings in my analyses over the last few weeks have just shocked me. They really have, and let me share them with you. Okay, so what we're talking about is a percentage increase in CO2 levels over a period of 134 years. And this is data that I was using. And this is, again, it's a massive data set, and so it takes monthly readings. So there's 12 data points for every year in that 134 years. So I can't do that math on the top of my head. So the data set is a pretty long spreadsheet. It is, let's see, 134. So it's 1,600 lines of data. Now, trying to get Excel on my MacBook Air that's about 9 years old can clog it up. So what I did was just kind of sampled data out of it, and I just kind of chose January. So what I did was I chose, and doing so because winter in half of the world, right? I took January data just so Excel could process it more easily. So I've got 134 data points, all from January. And I should tell you what this data point is. They're taken from multiple observation sites, temperature, CO2 readings, all these. There are registration sites, there are observation sites, many places around the world, and these data sets combine all of the data from those multiple sources to get. So if one sensor goes out, we don't have bad data. It gets averaged and sort of smoothed out that way. So it's all very, very good data. Okay, so first of all, just the basic kind of observational stuff, right? We're talking about over a period of 134 years, CO2 levels rising from 292 to right near 400, right, 395.8. You can see, using a polynomial best fit line, that there is a clear pattern emerging there. The R squared is 0.97. I mean, that's just almost perfect. So the polynomial best fit line fits really, really well, right? It's a best fit that's a great fit, right? And we're going to see what we can do with predictions with the various modeling approaches. Here we have added the linear equation. And R squared is still quite high, but not as good, because polynomial equations can just naturally accustom itself, or sort of fit itself to data better. But we're still talking about an R squared of 0.8677. That's really quite remarkable. So these are very clear patterned changes in the data. There's something going on, right? It's not random in any possible way. Okay. As I've said, we're talking about a 37% increase in CO2 levels over a period of 134 years. What I then did was, using that past data and the various equations, modeling equations that come out of polynomial and linear, to forecast 50 years into the future. What would or should we expect our CO2 levels to be in the year 2065, given that, as I've just said, the data, one of the things that R squared figure tells us is that those data are so non-random that the possibility that they occurred in that pattern by chance is just utterly remote, right? That gives us some grounds for confidence in the kinds of predictions we can make. Now, keep in mind that we're making predictions simply on the basis of past CO2 levels, and that there's we can do much better than that, and we'll do. Okay, but this is an appropriate place to start. So, using the polynomial equation to forecast CO2 levels for the year 2065, I come up with a CO2 level of 500 parts per million, which is, as I said, less than, but moving in the direction for the year 2100 of 880 parts per million that other forecasters have found. So the linear equation gives us a prediction of only 410, and I think it's pretty clear that the linear equation underestimates the rapid increasing, what do I want to say, the increasingly fast rate of adding CO2 to the atmosphere, and it's one of the most depressing things. I think it was. I think it may have been Lee yesterday. It was asking kind of, what has complexity science done for us, right? What is this knowledge? Has it achieved any victories? And I think it has, but I think it's also fair to say that we need to, be prepared to be humble and honest when we're not doing what we could be doing. And one way to do that is to point out that despite, all of the carbon agreements and efforts at carbon taxing and all of that stuff, we are, the first 2 decades of the 21st century has put greater levels of CO2 into the atmosphere at faster rates than the final decades of the 20. In other words, we're just getting worse, right? We're not getting better. And as we'll see in a minute, very soon, we don't have much margin for error. We really have very little time to make quite significant improvements in the condition of our atmosphere if we're to avoid a Venus outcome, a runaway greenhouse effect. Okay, so have I said so? The linear prediction, yeah. So we get a range of prediction outcomes, which is appropriate. Okay, so as I say, the one number I want you to remember is that one, 1.5 degrees centigrade, Celsius. Why? What's the deal here, right? Well, the Interplanetary Consortium of Scientists, climate scientists, have decided to determine in very significant, very influential report in 2017 or 18, that we basically have a maximum of 1.5 degrees Celsius that we can increase more the global average temperature, and not move past what we call a climate tipping point, a temperature tipping point. Right? In other words, we have only 1.5 degrees left to play with before we start doing irrevocably and severe damage to our environment that will threaten the extinction of human civilization. Right? So what's a tipping point? Well, as that diagram kind of shows you, right? I mean, it's basically got 3 features, a tipping point, right? This relates to complex systems in a number of ways. We can think about attractors, we can think about phase transitions, those kinds of things. A tipping point follows a period in which change processes were protracted, lengthy, and difficult, right? They weren't, movement up towards the tipping point wasn't made with ease, right? It was an uphill, as it were, kind of battle. But the tipping point is that point at which it is no longer challenging to move, to make progress, to advance. We start talking about increasingly powerful positive feedback loop, positive in the bad sense, right? And so then we flip over that tipping point and start runaway, whatever it might be. Runaway greenhouse effect is what we're talking about. We start rolling downhill, right? And there is just simply no additional effort required to continue to increase the speed at which we increase CO2 levels or increase temperature, right? And you end up with conditions like Venus. Right? And we don't want to live in a planet that's 465 degrees all the time, 24/7, right? Or whatever it is on Venus's orbit. 465 degrees Celsius is just a little too hot for life. Right? Okay, so let's kind of see what this kind of all means, right? We've got interactivities we've got to account for. We've got CO2 levels, we've got temperature, we've got 1.5 degrees left to play with, and then we hit that tipping point and boom, right? Game over, possibly, right? So these are the stakes, right? We're not playing small games here, right? So what I've done in the next slide is kind of construct a series of what I've tried to do is construct a complex systems model of tipping points, right? These points at which something dramatic shifts, those phase transitions, and it starts with this question of what difference does 0.5 degree make? So the scientific consensus is 1.5 degrees is all we have left. So what happens if we go past it? Because the problem here, and we must be honest about this, is that 1.5 degrees is the consensus that that's all we have left to add to our global temperature before we start doing serious and irrevocable harm to our ecosystem that threatens our existence. The problem, the additional problem, or the other half of the problem, is that keeping it at 1.5 degrees is almost nobody's belief. Okay? There's not many climate scientists who think that keeping it under 1.5 degrees is even remotely possible for human civilization. In other words, it's going to go to at least 2 degrees. So the question becomes, if 1.5 is consensus that that's all we get, what's 2 going to do? Right? And that's what I've tried to capture in this next slide. So just take a peek, just kind of watch it for a bit. Right? We've got water scarcity. We've got temperature in the middle, right? And we go past 1.5 degrees. We go towards that 2. We go past what we say consensus tells us is all we get. And that starts to feed into other tipping points. We start getting to a tipping point in water scarcity. And what's half a degree mean? The difference between 350 million people who are, imperiled rather by water scarcity versus 411 million people, just half a degree, right? Half a degree leads to a level of Arctic ice loss. That means it's gone all summer. And so that means sea levels rise. Just half a degree, from 1.5 to 2, right? Means a level of sea ocean rise that will wipe out entire civilizations, island civilizations. Coastal peoples will be increasingly threatened, right? And we're only talking about half a degree, right? Then we'll get, as a result of these things, it will lead to temperature fluctuations, including extreme waves of heat. Right? So though we've taken on the term climate change in preference to global warming, and we've kind of largely done so for political reasons, but let's just not, kid ourselves about what the real concern is, and then it's getting hot, folks. So the extreme manifestations of heat, right, will feed into another tipping point at which crop failures will start to happen at such a level that large numbers of people are threatened with food crises, with food security challenges, right? And so you can see how all of this feeds together, right? The crop failures also come from water scarcity, right? The water scarcity, right, is ironic given that we're seeing sea levels rise. We're getting more water in the ocean from the loss of ice, in part, right? And that all is putting more vapor into the air, the ocean level rising, which only increases the effect of the greenhouse. It's those vapors that keep the sun's warmth locked in and getting us a faster rate of temperature growth, right? So I'm afraid that my attempt here at a kind of a complex systems model of tipping points, right, is not very reassuring, because again the point is the consensus among the climate scientist community is that we only have 1.5 degrees left to play with. We can only afford to add another 1.5 degrees to the global average temperature before we really start screwing ourselves up. But no one seems to believe that only adding 1.5 degrees is remotely possible. It's just not in the cards. It's a minimum of 2 degrees. And so the question is imperative. What will going past what we have, learned is the max do to us? And it's not good news, right? Which is why the next slide looks this way. Right? This is what is at stake, right? Which direction do we go, right? Do we have a future that looks like Venus, a runaway greenhouse effect? Or can we muster the political will to do the things that we have the knowledge that tells us what to do? We know what to do. We have that knowledge-action gap, right? Can we muster the political will to save ourselves? Or, I'm sorry, folks, as I've said many times, it's not fair. It ought to be, if it's not, the great shame of my generation. We have bequeathed to you this challenge to save your lives, to save the planet for your children's lives, right? Because it's too late for my generation to do anything about it. It is really on your shoulders now. And that gives you, I think, a pretty clear picture of what your choices are. A future like Venus, or a future in which one can inhabit the only Earth, the only home we've ever known. So let's look at some data, some data here. Actually, I'm going to take a quick break. Okay, data. Look at some data. All right, so what we have before us is about what is it, about 140 years, I guess, of data. 130. Oh no, it's the same. Sorry, it's the same 134 years. That's right. I chose to make sure we had the same number of years of temperature readings as we had CO2 readings. So yeah, 134 years, 1880 to 2014. And these are, again, remember, this is temperature data expressed in, it's anomaly data, as it's called. So what that y-axis, the up and down vertical axis, is revealing is the degree to which the average temperature changed, and in what direction, positive or negative. Did it get colder? Did it get warmer? And by how much? So it's not the global average temperature that you're looking at. It's the amount by which that average changed from the preceding average. And that anomaly data is deemed much more helpful to us in observing the kinds of structural changes in climate, the signal rather than the noise, right? Because in terms of just data collection, what we're doing is not just, taking temperatures, right? We are smoothing out large numbers of observations of changes in average temperatures over time, right? So when something shows up, it's guaranteed to be real, and it's a signal, not noise, because of the way the data is collected and what it is that we're measuring. Okay, so what we have, in terms of kind of making just first observations, we have extreme, the highest values of lowering the average temperature change goes on close to a degree, negative 0.81 degree, right? And the next most significant decrease in mean temperature is 0.73 degrees, right? The other end of the scale, right, we have the highest values of increase in monthly average of 1.02 and 1.17, right? Now, what other observations can we make, right? Thinking back to yesterday in the conflict data, and I actually just kind of think about what kinds of observations can you make. I bet you can probably make that same serpentine observation, right? First of all, we're talking about over a 134-year period, a percentage increase, not in global mean temperature, but in the monthly average temperature change, right? Over a 134-year period, using just the January data points. If I had, a supercomputer on my desktop, I could have used all 12 data points for each of the 134 years and gotten even, tighter data. But it's quite good what I found, I think. We're talking about a percentage increase of 244%, right? That's a very significant increase in the average monthly temperature change in just a very short. Remember how little 134 years is when we think geologically, right? Okay. And so that serpentine pattern is there, right? But don't let the trees prevent you from seeing the forest. Remember Neil deGrasse Tyson and his lovely friend, right? What we learned from him is that don't watch the dog, watch the man, he said, right? The dog is going hither and yon. They're in random, chaotic, you can predict nothing, you can know nothing from that, right? That's just noise, right? But if you watch the man's path, right, you see a very clear direction cutting through all that noise. The signal is in all that noise. And that's what we've got in this data. So just drop the serpentine and look at the best fit line, right? The regression line here. And we've got an R squared of 0.6845. So it fits the data pretty well. We have a very clear, positive, linear increase of 244% over time, over 134 years, in the average monthly temperature change, a positive increase. It's Very, very significant, and it's that kind of finding, folks, that leads so many to conclude that 1.5 that we get is just a pipe stream. Right? Another observation is, right, if we take we're looking at a linear equation here, a linear model. We know already, right, the shape of what that polynomial trend line is going to look like, don't we? Right? Because it's clear as a bell, right, that these data are basically in two halves, right? There's a colder half and a warmer half, right? And the warmer half is the more recent half, and the colder half is the more distant half, right? So let's look, right? There's the polynomial trend line. R squared moves up to 0.726, so it's a very good fit. And it is on this basis that we can do some predictions, right? What should we predict for future temperature changes based on, clearly non-random data, right? So what I did was a 50-year prediction using both the polynomial and the linear equation, but just to kind of see the difference. So the polynomial model predicts in 50 years. What is that? Year 2065 or whatever it is. That in that year the mean temperature increase will be 2.5 degrees, right? Dwarfing in the amount of increase in temperature the total we are given to add to global temperature. That's a catastrophic event. That's a really depressing forecast, right? And it's based on an equation that fits the data rather quite well. R squared being 0.76, almost 0.8, is a very good fit, meaning there's a pretty reasonable basis for confidence in what we do predict, right? So what happens to our predictions when we move towards complexity, right?